In this video, we are going to discuss solve problem 9.4, which is about NASCAR racing. As a NASCAR racer moved through a banked curve, the banking helps the driver achieve higher speeds. Banking of road means when the edges of the road are elevated by an angle theta. And raising the edges of the road by an angle helps the driver take a turn at higher speed. The problem is asking us if the coefficient of static friction between the track surface and the car's tire is μs equals 0.620 and the radius of the turn is r equals 110 meter, what is the maximum speed with which a driver can take a curved bank at theta equals 21.1 degree? So let us first write down what is given to us. I have the coefficient of static friction mu s, which is 0.620. Then we have the radius of the turn, which is r equals 110.0 meter. And we have the angle of banking, theta equals 21.1 degree. We need to find what is the maximum speed v with which the driver can take a turn safely. So let us first sketch the problem. I have a banked road. The angle of banking is theta. Then we have a car on the road. Now the acceleration of the car is along the horizontal axis, like this, which is pointing towards the center of the circle. So when we choose our x and y axis, we have to choose them along the vertical and horizontal plane in this manner and not along the incline. Because when we were solving the inclined plane problem, the acceleration of the object was along the incline. Whereas in this situation, the acceleration of the car is towards the center of the circle, which is along the horizontal line. So we are going to choose our x and y axis as the vertical and horizontal lines. So this is my y axis, and this will be my x axis. Then we draw the forces acting on the car. The first force we are going to draw is the force due to gravity acting vertically down. I will call it Fg. Then we have the normal force which acts perpendicular to the surface. So this will be my normal force N. And then we have the force of friction, which is along the incline of the banked road. I will call the force of friction as small f. After we draw the forces acting on the car, we need to split all the forces which are not along the x-axis or y-axis. In this situation, it will be the normal force and the force of friction. So the normal force makes an angle theta with the y-axis, and force of friction makes an angle theta with the x-axis. So let's split them. I write a normal force along the x-axis as nx, along y-axis ny. And then we do the same thing with the force of friction along x-axis as fx and along y-axis as fy. Then we can write the forces here. Y component of the normal force will be written as n cosine theta. X component nx will be n sine theta. Whichever component is attached to the angle theta, that component must be written as cosine of the angle theta. So here my y component of normal is attached with angle theta. So I will write the y component as n cosine theta. We do the same thing with friction. The x component of the force of friction is attached to the angle theta. So the x component of friction will be f cosine theta, whereas the y component of the force of friction will be f sine theta. After we identify the forces and split them, we will write the equation of net force. When we write the equation of net force, we have to write the equation separately for x-axis and y-axis. Now, since my car is not accelerating along y-axis, the net force acting along y-axis has to be equal to 0. And the net force along y-axis will be sum of all the forces along y-axis, which will be the y component of normal force, y component of force of friction, and the force due to gravity. So let us write them. I will write Ny, which is n cosine theta, minus the force of friction, which is F sine theta, minus the force due to gravity, Fg, equals 0. Now, the reason we take the y component of friction and the force due to gravity as negative because they are going down, they're going along the negative y-axis. When we write the equation of forces, we take all forces going up to be positive and the ones going down to be negative. So the direction we will choose as before, all forces going up and to the right, we will take them positive. All of them going down and to the left, we will take them negative. Then we rewrite this expression. We know that the force due to gravity Fg we can write as m into g, and the force of friction is written as mu times the normal force. So let's substitute that here. N cosine theta minus mu n sine theta minus m into g equals 0. Rearrange the term. I will move mg to the other side. N cosine theta minus mu s n sine theta equals m times g. We will call this equation 1, the entire expression as equation 1. Now we do the same thing along x-axis. Along x-axis, we know all the forces which are acting along the horizontal axis is giving me the required centripetal force to keep the car along the curved path. So sum of all forces along x-axis would be equal to the centripetal force needed to keep the car along the curve. So we write for x-axis F net x is equal to the centripetal force Fc. So along x-axis, we have the x component of normal force and the x component of friction. And we write that n sine theta plus F cosine theta is equal to centripetal force, which is mv squared over r. Again, for the force of friction, I'm going to write it in terms of the normal force, mu s normal cosine theta, which is equal to mv squared over r. This is my equation 2. I need to find what is the maximum speed way with which we can safely take the turn. And to find that, we are going to divide equation 2 with equation 1. I'm going to do this step so that we can calculate for v. So let's write equation 2 first. Since n is present in both term on the left hand side, I'm going to take n as common out here. Then we write whatever is left, sine theta plus mu s cosine theta is equal to mv squared over r, divide by equation 1. Again, in equation 1, we are going to take n as common outside or from the left hand side. Then we write cosine theta minus mu s sine theta. And then we have mg here. So multiply with mg at the bottom. Then we can cancel off the common terms. I will cancel the m here from the top and the value of n here. After we cancel the common terms, we are left with sine theta plus mu s cosine theta over cosine theta minus mu s sine theta equals v squared over rg. Now we need to find v from this expression. So you can either use shift solve in this equation over here to calculate for v. I can substitute all the values given to me from the equation, or we can rearrange the term and then solve for v. So when I have to rearrange, I need to keep v square alone on the right hand side. In order to keep that alone, I'm going to multiply with RG on both sides. So when you multiply with RG, you get R times G into sine theta plus mu S cosine theta divide by cosine theta minus mu S sine theta equals V squared. And when you have to find V, you need to take square root on both sides. So we get V equals square root R times G sine theta plus mu S cosine theta over cosine theta minus mu S sine theta. Now we can substitute our value and solve for V. So we get square root. This small r is the radius of the circular path, which is the same as capital R over here. So I'm going to substitute that as 110. G is acceleration due to gravity, so 9.81. Sine of 21.1 plus mu is 0.620. Cosine 21.1 divided by cosine 21.1 minus again mu is 0.620 sine 21.1. And when you solve this, you get the value of speed V as 37.77, which you can round off to 37.8 meter per second. So this is the maximum speed with which you can safely move around the curve.